All right, let us begin with the lecture. So last time, yesterday, we ended off with this true or false discussion. And we already saw that the answers to these true or false questions gave us corollaries of the dimension theorem. And so today I'm going to start with this discussion. And the overall plan for today, and we have 2 hours today, is going to be to also get to the composition of transformations and the inverses. I'm not certain that we'll finish both topics, but maybe we can at least get started with the inverses. And this is week 6. The new version of these notes, including the last section, I just pushed to the GitHub, and I'll add to Quarkus later. Okay, so for now, let's discuss, to get back into the topic, let's discuss this. If you have a transformation, linear transformation between two vector spaces V and W, how do the dimensions of V and W obstruct whether T can be surjective? So compare this to corollary 244. And this corollary said that a linear transformation can only be injective if the domain has a smaller dimension than the codomain. So if it's going into a bigger space, then it can be injective, otherwise it can't be injective. So now just think about for maybe 2 minutes, what about surjectivity? And we've had something, maybe we've already discussed something along these lines. And this proposition 2.4.7 might also come in handy. It said that the linear transformation is surjective if and only if the dimension of the image is equal to the dimension of the codomain. All right, any ideas from anyone? Yes, Jancy.
So I think V should be less than or equal to W, because by the dimension theorem, V equals to the dimension of the image plus the dimension of the kernel. And since it's surjective, we know that the dimension of the image is the dimension of the codomain.
Yes.
And the dimension of the kernel is positive, or 0, or any positive number.
Yes. Yes, indeed. So as Jancy said correctly, we need for surjectivity, so desk just feels too small. Second. Maybe I should mute myself when I move the microphone. Okay. Yes. So for surjectivity, it is correct that we need the dimension of the image of T to be the dimension of W. And we know that the dimension of the image of T by this dimension theorem has to be smaller or equal to the dimension of V. So because the dimension of the kernel can't be negative, we know that the dimension of V is always greater or equal to the dimension of the image of T. And you can also intuitively think about this as that V is inserted into W, and maybe it is compressed, but you can never make the image bigger than V. So if you, for example, if you embed the plane, if you map the plane into R3, then you could maybe lay this out as a plane like this. You can also map this just onto a line. You can compress everything just to the single origin point if you want. But you can never blow this up to 3D. So you can never make something 2D map into something 3D that's sensitive to everything. And that's kind of the idea behind this proof. So this proof is just making it rigorous what I just said about this idea. So we know that the dimension of V is always bigger or equal than the dimension of the image of T. But we want for surjectivity that the dimension of the image of T is equal to the dimension of W. So we need that the dimension of V is greater or equal to the dimension of W. Otherwise, we would have no. Let me just stop here. I mean, if you connect these two equations here, this with this, so the Selman color is this is always true, and this is what we want, and then we would naturally get that this has to be true. Any questions? Yes, Oliver.
So it will be. Can you just re-clarify again? Sorry. So
yes. So I said that this pink equation here is always true from the dimension theorem. That the domain can't be enlarged in the dimension when we map it to another space. So the image of the transformation always has to be less or equal to what we started with in V. It can't be like you can map a plane to R3 and make it bigger than 2 dimensions. So this is always true. And this one is what we need for surjectivity. This is for surjectivity, we need this. This is just the previous proposition that we ended up with yesterday. This is just something we proved.
Mm-hmm.
And so if you combine these, if you combine these equations, you just chain them together, then you get that the dimension of V has to be greater or equal than the dimension of W.
Okay, and that's the conclusion. Okay.
Yes, exactly. And so only if this is true we can have surjectivity, but maybe a remark is that dimension V greater or equal to the dimension of W doesn't mean that T is surjective. I mean, you can always send everything to 0. So you can have that R2 to R3 sends every vector X to 0. That is the transformation. It could be like there could have been surjective transformations, but this one is not. Same with injective. If we have this condition that it might be injective if and only if the dimension of the of V is less or equal than the dimension of W, it's not guaranteed that every transformation will be injective. All right, so let us quickly let's quickly prove a proposition, namely that if we have a transformation which is injective and surjective between two vector spaces of the same dimension, then it is, I want to say that it is injective if and only if it's surjective. But this is not a very hard proof, because so suppose suppose T is injective. Then this means that the dimension of the kernel is equal to 0. And this means that the dimension of W, which was assumed to be the dimension of V, which we assumed in the statement, is equal to the dimension of the kernel of T, which is 0, plus the dimension of the image of T. And so if we look from the, if you compare left and right side of this equation, then this means it is surjective. So injectivity implies surjectivity as long as we have that it is going between vector spaces of the same dimension. And now if we suppose that T is surjective, then I guess the best way to write this down is that the dimension of the kernel of T is always the dimension of V minus the dimension of the image of T. This is just by the dimension theorem. But by surjectivity, which we assume in the second and the converse direction that we want to prove, that the dimension, this is exactly the dimension of W. So this is the dimension of V minus the dimension of W, and this is 0 by assumption. I could give this assumption a star and put a star wherever I use this. Yes, Idris asked whether this means it is bijective, and it is absolutely true. So basically, this proposition is supposed to help you when you want to show that something is a bijection, and you know the dimensions of the domain and the codomain are the same, then it is sufficient to only check one of the two things. We had a similar thing. Remember that I had this proposition in the lecture that said if you have a vector space of dimension n, and you have you have a family of n vectors, then it suffices to only check independence, and spanning automatically follows. This is the sign. This is the same spirit. That you have to technically check two things, but if in a certain condition, namely this one, then just one of them is enough. All right, let's see. So this example, I think I want to skip. Maybe I'll get to this another time, but it's not very illuminating at the moment. And in fact, yeah, let's look at this discussion. And yeah, so I wanted to argue whether this is injective or surjective. Without actually doing the computation or any computation. And I guess I forgot to add here that you should do this for different n. I think it's best to look at the cases n equals to 1 and n equals to 2. So let us think about these in particular. I honestly, yeah, I think that this is the best way to think about this. And this means, I mean, some computation has to be done. You can't do this completely without math. Okay, let's discuss this. And I have to admit that I kind of forgot the upshot of this thing. Like I was kind of confused for a little bit why I was asking this, because yeah, I mean, there's something to be said, but let's just start and see where we go with this. So the difference, I mean, remember that we had this evaluation map that sent the polynomial p of x, say evaluation 5 to p of 5. This is the same idea. Only this time, what we want to do is we want to evaluate it at 2 different points and consider the pair of these points together in R2. So for n equals to 1, can it be injective? Can it not be injective? Is it injective actually? Is it surjective? What can we say about this? I mean, as soon as I said that, I kind of forgot why I put this in here. It's totally fine if you just have a vague idea or a comment that you want to make and so on. It's really just the purpose is really that we train to think about situations and the concrete examples, and this is a very concrete function that we can consider. So Andrew said it is bijective for n equals to 1. And yes, that is actually true. So why can we conclude that this is bijective? Let's start with surjective. I think that's the easier one. So I've already drawn something in the top right corner, and let's say we have any point y1, y2 inside R2. This would correspond to 2 points, 2 values that we want the polynomial to have. So if this is y1 and say this is y2, then the idea is that we want to have a polynomial of degree 1, which is just a line which does not necessarily have to go through the origin. And we want to find, so this is surjective, means that for every pair, or for every 2 tuple, y1, y2, there is a polynomial p of x such that p of 0 is equal to y1. Oh, and I should be more specific. P of x is equal to ax plus b, such that, so this means it's a line, such that p of 0 is equal to y1 and p of 5 is equal to y2. And when I wrote without computation, what I really just mean is, well, there's nothing really to be computed. You could just draw a line through these points, and then that will be this will be a polynomial of degree 1. So this is indeed true, and we could do some math, but it should be really clear intuitively that you can, when you specify 2 points, it's always possible to find a line through these points, and that will be some polynomial of degree 1. Okay, and now comes the real reason why I put this in here, I believe. If we talk about injectivity, injective, then this is really, it's really helpful to look at the previous proposition, because we can notice that the dimension of P1R of all the degree 1 polynomials is equal to 2. And this is also the dimension of R2. So by the previous proposition, surjective implies injective. And we're done. So there's no need to compute the kernel of this map or to check whether 2 maps, 2 polynomials that send the value to the same points are actually the same polynomials. It's enough to just use this proposition that we just stated here. Okay, this was, I guess, the main reason why I wanted to put this discussion in here. But let's just also just briefly think about n equals 2. Any comments for the case n equals 2? Yes, Andrew, that's right. Because, so Andrew said that if we look at, let's draw this again. We have the points 0 and 5. So now we're allowed to not just use lines, but we can use any parabola. I think it's a coparabola. So let's specify 2 values, say this and this. And I mean, we could in particular take a line, but we may also be allowed to like use something like this. It's not very pretty, but I think you know what I mean. But in fact, yeah, Matthew just commented something very important. So now there's a multitude of polynomials of degree 2 that go through the same 2 points, and so it is still surjective. Switch slides. Surjective, but not injective. And I'm just going to refer to this this diagram for an argument, like for reasoning. Any questions? All right, so we're about to end this section about the dimension theorem and its applications. And there's one more idea that I thought I don't want to include for time reasons. It's very interesting, but it's not crucial for the trajectory that we're on in this course. So if you are interested, and maybe I'll talk about this later, maybe it will be important later, but so far I think we can just exclude this from our syllabus. This is proposition 2411, and it basically it makes it more formal what the solution space is. So remember that I was saying that the solution space to ax equals 0 is kernel of the transformation of T sub A. So now the question is, what is the solution space to ax equals to b for b non-zero? And this is exactly what this proposition is trying to answer. And then you can also look at this example. If this should be part of a test in the future, then I will talk about this again, I guess, or I might just talk about this again if it's not part of a test, and if I feel like we have time to talk about this and it fits in. But for now, I don't want to spend time on this particular idea. Okay, so this is the end of the dimension theorem. I think we've seen quite a bit and talked about we've done like different gymnastics with this. If there's no questions about what we did in this section, then I want to move on to composition, because this is something very, very essential and crucial that we need to talk about. Okay, so a composition, I think I've already mentioned this in the very first week in the basic section of the preliminaries. A composition of two transformations really just means that you concatenate them. So it means that if you have two compositions where and this is very important, where the codomain of the first transformation is the domain of the second, then you're able to feed the results of the first transformations. So when you have S of U for U in U, you're able to apply T to the result of S. So this means you can write T of S of U. And if you do this, if you just go from U to S of U, and then from S of U to T of S of U, we just want to give this a name if you go directly from U to that result. And this is just called T composed S. So I've written exactly here that, that we consider T composed S is a new transformation which exactly just is the concatenation of S and T. Notice that the order of writing T composed S is by the order that you apply it. So the S is the inner transformation that's applied first, but it goes from right to left, and not like this is something you just have to get used to. And the very first question that might come up is whether the composition of two linear transformations is again linear. And we're lucky that it actually is linear. And the proof is not particularly hard. Let's just look through this. So there's two things you need to check. We assume S and T are linear. So this means two things, that S of x plus y is, it means that S of x plus y is equal to S of x plus S of y. And if we have alpha times x, let me not use alpha, but maybe c, and you apply s to this, you'll get c times s of x. And now we want to show this for the composition. So this means we have to check two things. We apply T compose S to a sum of vectors x plus y. And so by definition, this really just is T applied to S, to the results of S of x plus y. But now what we can do is we just apply linearity for S. So we can modify the inner part. This is T of S of x plus S of y. And now we have T applied to a sum of two vectors. So now we apply this linearity assumption for T to this sum. And then what we get is T of S of x plus T of S of y. And now we see that T of S of x is really just T compose S of x. So this is T composed S of x, and this is T composed S of y. And this is linearity for T composed S. Let me just skip the second part, but it's very similar. You just apply this twice for the assumption, and then you'll get the result. So you would start to compute C times X, and you can see how this works. Oh, Idris has a very interesting question. So Idris asked whether the order can be switched. Let me just throw this back to the class. What do you guys think? Can it be switched or cannot be switched? So let's look here at what happens if you have V. So U from S goes from U to V and T goes from V to W. Does it make sense to say T to write T composed S of, I guess, V? Yes, so it doesn't make sense unless W and U are equal. So this does not make sense. This is because if the vector V lives in here, then this means T applied to V will live in this vector space. But S, I mean, that was the reason that we introduced this notation. So this means S can only be applied to elements in U. And this might not be equal to W. So this is not allowed. But that's a good question, because I was going to say this anyways sooner or later. Okay, so actually I was supposed to write an example on number 1, but let's just skip that and go to number 2 directly. So one example is no, let me still do example number 1 because I think it's important to start with an easy example, and then number 2 is already intermediate, I guess. Can I put this somewhere? Let me put this up here as a remark. So this is a warning. Don't mess with transformative of composition. Okay, so example 1, and I was just lazy, I didn't want to type this out in LaTeX, so I'm just going to write this here. So suppose that we have, I want to compose the transformations are going to R2, and this sends the number x to 2x and minus 3x with another transformation, and this one is going from R2 to R, and it sends a tuple xy to x plus y. And then so what is T composed S? Any ideas? So this is just the very first example. It's not very involved, but I think it just should get you started off of the idea of composition. So first question, what can we apply this to? What's the valid input? Yes, the result is the answer is correct. So we can only apply this to x because remember from this diagram here, T composed S has to go from the very left to the very right. So it skips the V. So here the T of S will go from R to R. It will skip the R2. So it connects it's like a domino, it goes from here to here. So what this is it's T of S of x, which is T of 2x minus 3x, and this is then, and then we interpret the first component as x and the second as y. So of course there's going to be I could have used maybe u and v here, and then it's going to u plus v, but you really have to pattern match that the tuple that's sent to here will be the tuple that's expected here as an input. And then this is 2x minus 3x, and this is indeed minus x. So really what this composition does is it just sends a vector, like a number, to minus itself. Okay, very good. So let's look at the second example. So the second example is again is already a little bit more involved. So I'm defining here in these two lines, I'm defining what I would call the translation operator. Like it's actually does anyone know anything? This is not linear. I just realized that while I was explaining this, that this is not a linear transformation. This is unfortunate. So I guess, yeah, in order to avoid confusion for the future, let me just avoid this. Can I screenshot, copy this, paste it in here. And then let's just pretend that this never happened. Okay, I'm gonna have to find another example that's making up for this, I guess, but yeah. Okay, so let's look at the number 3. I'm going to delete this in the LaTeX later. Okay, so number 3 is actually a valid example. We've seen that the derivative is a linear transformation. It takes a polynomial and it sends it to another polynomial. So p of x is sent to d by dx p. And if we apply this again, if we do d by dx of p of x, then we have d by dx dp by dx of x. And if you take a derivative of the derivative, we're going to get the second derivative. In this case, the domain and the codomain are always the same. So in this case, the order doesn't matter. In fact, if you would have, no, never mind. Let's just move on to this discussion. And here I have I've made a proposition from the book into a discussion because I think it's not very hard to argue. So I just want you to discuss this proposition, and I'm gonna fill in the blanks, or we're gonna see why this is true. I'll give you 3 or 4 minutes, and if you have questions, then just write in the chat, or maybe I can just like state what this means. So the idea of this statement that you want to discuss is, if you have 2 compositions, if you have 2 transformations and you compose them because they're composable, then this means that if you go from u to v, or if you go from u already all the way to w, then you have t composed s and s. So they're both transformations that start at u. They both take values in the same vector space. So this means the kernel of s is a subspace in u, and the kernel of ts is a subspace in u. And I want you to argue why the kernel of s is always containing the kernel of t composed s. And likewise for the image. So if we look at at w, there's 2 transformations that arrive at w. So there's 2 transformations for which w is the codomain. And so we have the image of t and the image of t composed s both in here. And I want you to argue why the image of ts is always inside the image of t. Okay, I have to close the blinds. I'll give you 3 minutes. Okay, let's see what you have. Adrian.
Yeah, so for the first one, I think we can just start with any vector x in the kernel of S.
Okay, so I'm going to pick x in the kernel of S.
And then we know that if we apply S, we get back the 0 vector.
That's correct.
And then we can also show that if we take t of S of x, then we just get back t of the 0 vector. And then just by linearity of t, that has to be the 0 vector as well.
Yes, indeed. Let me just turn your line.
Yeah, and then basically just the t of S of x is just a definition of t composed S as well, of x. And therefore, it's just also an element of the kernel of t composed S.
Yes, very good. So this means we've shown that t composed S sends x to 0 based on our assumptions. And this means that x is in the kernel of t composed S. Yeah, that's already it. Any questions about this? Like the intuition about this is that once S sends something to 0, T can make this like undo this. So you can't send anything that is already 0 to something non-zero. So once S decides that something has to go to 0, T has no choice left than to send this to 0 as well. Okay, what about the second part? Andrew.
So I guess we can start by saying that the image of S is a subset of V.
Yes.
And
yeah, so go ahead.
Yeah, so since the image of S is a subset of V, the image of T composed with S should therefore be like a subset of the image of T, because T takes the entirety of V and sends it to W. And that, like, since the image of S is a subset of V, it's a portion of V that gets sent to W. So therefore, that's also a subset.
But we're interested in the image of T. So we want to relate the image of T and the image of T composed S.
Yeah, so since the image of S is a subset of V and T sends every single vector in V to W, shouldn't that by linearity imply that the image of T composed with S is a subset of the image of T?
I mean, I'm just trying to be careful not to skip any details, not like say it's clear or obvious without actually having checked every detail. So you're saying that so because T of V, which is the image of T, is inside and W.
Yeah.
Then in particular, every element in S and in the image of S. So you're saying, say, V is in the image of S, is sent to T of V in the image of T. But I'm not convinced. Maybe I'm missing something, but I'm not convinced that this is enough to show that every element in the I guess you could So I'm not saying like that what you're saying is wrong. I'm just saying that I'm missing like one detail that I would like to include to make it clear from start to finish. And I guess what I would like to add is that if you have something in the image of S, a vector V, then it is in particular this will be S of some vector U, because it is in the image of S. And yeah, so let me just start over and explain it. I'm not saying that this is wrong. I'm just saying that I'm missing steps, and I'm getting confused if there is if I can't like see this from start to finish in detail. Maybe afterwards you can tell me whether this is the same that you meant, or whether there's some difference. So
Yeah. Sorry, I think I skipped some steps like during my reasoning.
Okay, we can compare in the end, like, and then fill in the blanks. Maybe that helps you to fill in the blanks. So whenever I want to show an inclusion like this, the standard procedure is to pick an arbitrary element in the smaller set and show it's in the bigger set. Like that's my, like, I have this urge to start this way. So pick any element, say W, in the image of T composed S. And because it's in the image, it means that it's hit, it's sent there under T composed S. It's actually sent, like some other element is sent there. So this means for some U and U, we know that W is the image of U under T composed S, which is just T of S of U. And so this means, therefore, S of U, which is a vector in V, is sent to W. That is, W is equal to T. And now I'm trying to emphasize, let me call this V, that V, which is just S of U, is exactly a vector that is sent to W by V by just forgetting that S already was applied to U. And so W is in the image of T. And in conclusion, we've shown that that every element in the image of T composed S is in particular an element in the image of T. Does that make sense?
Yeah.
Okay. Yes. So maybe you could have like maybe done this without picking the elements. Like you could maybe have like a more elegant short solution, but just for the purpose of clarity, I also want to just make sure that every step is clear. All right, it's time for a break. Let's take a quick break, and then we'll define matrix multiplication afterwards. See you in 5 minutes. Let's keep the recording. Yes, it's going. Thank you. Okay, and now the cool thing is that if we add to this picture another transformation that we can post compose with S. So this is T, and now this is going so we can apply T after S. Then there's transformation that then there's a matrix going from Rn to Rp such that this matrix T, the matrix of T, beta, sorry, they called the basis. No, this was completely correct. Alpha, beta, and then beta, epsilon. Well, epsilon is the basis of these are the bases. Okay, so I don't want to make this diagram too confusing, but the idea is that if you start with an n tuple in here, and you go to create a vector, and then you apply S to the vector, and you look at the n tuple of the results, then this is just done by matrix multiplication. Now, if you have this n tuple in Rn, and you go back to the vector and you apply T, and then you look at the resulting p tuple. This is done by matrix multiplication. So the idea is that the matrix that's given that's representing S composed T composed S should depend somehow on the matrices that represent S and T. And so if we have this vector, let me just say that by definition, S, the matrix representing S is the matrix such that so this is gamma alpha of the vector u, that if we have this, if we have a coordinate tuple of a vector u, which I'm just going to denote by u sub alpha, then the coordinate tuple of S applied to u in the basis beta is supposed to be the matrix times vector product S alpha beta of the tuple of the coordinate tuple u alpha. So now if we do this, and then this will be the n tuple of S of u. Now, if we apply T to this, then there's another matrix that's exactly taking this as an input and sending it to the results of T of S of u. So the matrix T beta epsilon takes the n tuple of S of u and sends it to the p tuple, the p tuple, which is the coordinate p tuple of T of S of u in the basis epsilon. But this is going to be just T beta epsilon S alpha beta u alpha. So you see that that the same way that we compose transformations, there has to be some composition of matrices as well. And the idea is to now define what is this composition of matrices in a way that if we have a composition of transformations with matrices representing them, then the composition of transformations should agree with the composition of matrices. So and from this bottom line here, this is really the important line. The composition. Any questions so far? What I said? Kind of second guessing now the plan to introduce matrix multiplication in this way, but we already at this point, so let's just continue. So I'm saying that an M tuple is a vector with M elements, and a P tuple is an element with P elements. I'm just using different M, N, and P because the dimension of U, V, and W might not be the same. All right. So even if that was completely ununderstandable, like completely confusing, let's try and just erase your memory of the past 10 minutes and let's start fresh again. Otherwise, don't erase the memory. So if we have two matrices, and this could be these matrices representing transformations, then the product of the matrices A and B should be something such that if I apply this to a vector, if I multiply this new matrix, so this is supposed to be a new matrix, such if I apply this to the vector x, then it should be giving me back the same vector as applying first b to x and then a to x. So AB is defined by this property. If I multiply AB with a vector, this is supposed to be the same as A multiplied with a vector that we get by multiplying B with X. Okay, any questions? So I have to find something for two matrices, but I'm not really sure what this is. So now comes the important part. And this is what I mentioned yesterday, that some professors' definitions or other professors' propositions, because now I'm going to be like, because I'm requiring that matrix multiplication is exactly that the thing that does this job. I can actually prove that this is the way to actually get this definition, to actually get this this product. Okay, how am I going to prove this? So remember that. Right, so let me first tell you what this proposition is that we're trying to prove. So what I'm saying is that if you have two matrices, and I'm going to draw in the intuition section picture. So if you have two matrices, this is the matrix A. So this is entries A11, A12, and so on, A21. And I have another matrix B with B11 and so on. So somewhere there's some B a BKJ. So this means that this is the jth column and so on. Then the resulting matrix, which we're going to denote by AB, is supposed to be a matrix again with elements. So let me just denote them by C. So this is going to be C11, C12, C. Yeah, it doesn't. I'm going to fill this in later. And so the question is, what are those elements? So how does the ij element in the ith row and the jth column depend on the previous elements in A and B? What I'm claiming is that if you specify the indices I and j, and this is the element, this is Cij is the element in the jth column and the ith row, then you have to look at all the elements in the jth column of the second matrix in the product, and the ith column in the first matrix in the product. And that what you do is you just write that that Cij is going to be the first element in here, which is going to be bi1. Let me close them later. So that's going to be bi1, the element in here, and the element in here. You just multiply them together. So you have aa1 bij, and then you take the next two elements, so the second element in this column, and you multiply this with the second element in this row. So you basically perform a dot product between the column here and the row here. So if I keep writing this, this is going to be ai2. This is the second element in the ith column. So in ai2. And you multiply this with b2j. Let me now actually zoom in here and give you more details. So this is going to be b1j, b2j, b3j, all the way to bnj. This is the jth column. And here what we have is we have, of course, it's not going to be under this, it's going to be ai1, ai2. So the only thing that's constant is the first index for the row, and then we're going to have ain. So I'm going to pick I'm going to pair these together. So this one goes with this one goes with this, and so on. And then when I multiply them and I sum up the result, this is basically just the dot product of these columns and this column and this row as a vector. Then I claim that this is the result. This is going to be the Cij element. And so this equation in shorthand is just written up here, that that the Cij, the ij element of the matrix AB, is going to be a sum of A's and B's, namely the ones with a fixed. So here in this equation, the I and J are fixed, and only K varies. So K is going from not 0, but rather 1 to n. Any questions so far before I don't know, I probably should improve this. Any questions so far? Okay, so let me not prove this right now, even though the proof is very interesting, and the fact that it works out. But I think it's not very illuminating if you see this for the first time. Instead, let me go to an example, and actually let's make this a discussion, because I feel like I've talked enough in the past 20 minutes. So we make this a discussion, and I want you to compute the matrix product of 2 minus 3 1, 5 0 minus 2, product with 1 2 2, 2, minus 2, 3. This should give an interesting result. So take 3 minutes or so, and then tell me what the answer is. Okay, can someone tell me what the result is going to be? -6, 1, 9, and 4. Yes, that seems to be the majority. Like if this was democratic, then this would be correct. Let's see how we get this. So first of all, well, this is going to be a 2 cross 2 matrix, and we're going to have C11, C12, C21, and C22. So why is that? The number of columns, the number of columns in the second matrix will determine the number of columns in the result. So therefore, there are two columns in the result, and the number of rows here will determine the number of rows here. So if I had given this another column here, then we would have another column here, and this result would be longer. This is really just this is the how it works. And then I told you that C11. Okay, let me just write a bigger matrix. So to compute C11 and the top left here, what we do is we multiply just this number with this number, so it's 2 times 1. Then we have -3 times 2 plus 1 times -2. Let's see, this one has space. And this is going to be 2 minus 6 minus 2, so it's going to be minus 6. So you just asked a question whether the order matters when multiplying. So if you mean the order of these numbers here, then no. But I think that should be obvious, right? Let me just finish this, and then I'm going to address this question in a second. So the next spot, this C12 element. Now I told you here, if you want to have the ij element, you have to take the jth column and the ith row. So this means for this, what we need is the second column here, and still the first row. So now we have to pair these two together. This gives 2 times 2, minus 3 times 2, plus 1 times 3. And so we see that this is 4 minus 6 plus 3. So this is going to be 1. Now, if you take the 2, 1 elements, we take the we have to compute. We take the second row of the left factor, the lower one, and we take the left column, and then we get 5 times 1 plus 0 times 2 minus 2 times minus 2. This is going to be 5 minus 4, which is 5 plus 4. It's going to be 9. Yes, you got the same result. And finally, in the bottom right, now we take the right column and the bottom. So this is going to determine, like, this is the second row, second column, and then we get 5 times 2 plus 0 times 2 plus minus 2 times 3. This is going to be 10 minus 6, and this is going to be 4. All right, and this is the result. Now let's address Idris' question. So what if we change the order of these? So what if I told you to compute the matrix product of 1, 2, 2, 2, minus 2, 3, with 2, minus 3, 1, 5, 0, minus 2. Would this be the same? Would this be different? Would they be somewhat related? Notice now we have 3 columns in the second, and we have 3 rows in the first matrix. So this would be a, yes, indeed, a 3 by 3 matrix, and it would be just completely different numbers in the matrix. So we have 3 here, 3 here. And I'll just leave it as an exercise for you to go through this and just compute this. Any questions? So this proposition that I postponed the proof of basically just says that if we now define matrix multiplication to work in this way, then so the goal, or the idea of this definition is that if we have composable transformations, and as always, when we're calling them S and T, we have that the matrix, and these have bases alpha, beta, and epsilon, say that the transformation that is T composed S the matrix representing T composed S is going to be equal to the matrix representing S matrix product times the matrix representing, oh, sorry, other way, T times S. Now you just have to fill in the bases. So of course, if you have a transformation T composed S going from U to W, the bases are going to be alpha and epsilon. T goes from the basis beta to the basis epsilon. So we can write beta epsilon, and S is going from the basis alpha to beta. And the kind of way that I presented this, the last 2 pages. So we defined matrix multiplication in exactly the way that this is true, or that this holds. And so you can think of you could have defined matrix multiplication by this, but then I guess some would have asked why this? How did you come up with this multiplication rule? And now the explanation is, well, I wanted to have a composition of matrices. I want to have to compose 2 matrices into a new matrix in a way that it agrees with composition of linear transformations. And that's the honest answer. This proof is really nothing, it's not adding anything to the story. It's just something we would have to do formally to make this argument solid. But in this case, I guess I'm going to just skip this and we're going to look at examples now. Because I think this is more valuable to actually look at examples. Okay, so let's do a discussion. I think we have time for 2 more discussions. And then, yes, so I think we can wrap up composition in this lecture. And then next week, we're going to start with the inverse. So this discussion, let me remind you that the rank of A, I'm actually not sure if we defined this properly in this lecture or whether I just hope that you had this in 223. So the rank of A is equal to the number of leading ones in the reduced row echelon form of A. And this turns out this is the same. And I guess this is not obvious, but we would have to prove this. This is the same as the dimension of image of the transformation given by A. So I'm just going to give you this as a refresher. And now please discuss if you have 2 matrices A and B. Oh yeah, let's first look at this. What does it mean to be composable? So for transformations, we said they have to have, so for transformations, if you have a transformation going from U to W, or say U to V, and then W to Z, they're composable if V is equal to or contained in W. It doesn't matter if it's not the whole space, because you can just restrict T. You can just say, well, let's just restrict it to a smaller subset. And here, composable means let me for this purpose just say that it has to be equal. And for matrices, composable means that that you have an m cross n matrix. You have to multiply this. You can only multiply this with an n cross p matrix. So here, for transformations, you need that that these spaces are the same, and for matrices, you need that these numbers agree. And this is really just, you can also add that, so then if this is composable, then A times B is an M cross P matrix. So it really means that that you match these two ends, and then you just make a new pair M cross P out of this. And the reason that that this is composable, that you have to have this compatibility to be composable, is really just obvious from the definition here. If you wanted to pair, say this first column with this first row, then you need the same number of elements in this column as in this row. So this definition that I gave here of this sum of AI1 B1J doesn't make sense if there's more A's than B's in the row than the column. And here, this is the size m. That's the number of rows, and the number of columns here is n. And n is exactly the same. Is the number of rows, the length of each column in B. So these have to match. And then the result will be an M cross P matrix. So this is going to be an M cross P matrix. Okay, so let's get to the discussion. Why is it true that the rank of A, is the rank of A or the rank of A times B possibly greater? Okay, so I don't know if this discussion is too hard to answer, or whether this is whether I'm expecting there too much. But let's just discuss this, and don't be afraid of giving wrong answers, or just like partial answers, or just ideas. Okay, Andrew said in the chat that both can happen. Were there any other comments? Zach said that A has a greater rank, or the same, and that's correct. That the rank of A is always greater or equal than the rank of AB. So now the question is, how can we show this? So let me write down the claim. The claim is that the rank of AB is always going to be less or equal than the rank of A. And the way that we can prove this is just by a series of observations. And this is the point where I just realized maybe these observations are not easy to go through. Like, it's not easy to get these ideas. So first of all, but if you have an idea in the middle of this discussion now, just like write this in the chat, or just like comment on what you think. So first of all, if you have TA, so A is an M cross N matrix. Then we can define TA is the transformation going from Rm to Rn. This is the linear transformation defined by TA of a vector x. So x is in Rm. Is just the matrix product A times x. And the same is true for B. We run out of space very, very quickly. Anyways, so now why is this helpful? So if we compare, if we now have a matrix B that is composable, this means that B has to be a matrix of size n cross something. So I'm just gonna say that B is an n cross P matrix. And so this means that we can write T B composed with TA of x. This is going to be TB applied to A times x. This is going to be B applied to A times x. But by the definition, this is going to be the matrix product. This is going to be, did I mess this up?
Yeah, I think the transformation goes from Rn to Rm.
So this is Rn to Rm. I'm honestly confused around, because if you have a matrix that has, I called this M, this is M, this is N, so it should go from N to Rn. But then shouldn't this be of size? Oh yes, absolutely, yeah. I confused myself for another reason, but that's fine. So this should, thank you for everyone who noticed. So this should be N to Rm. And the way that I write this, I can post. Why does? Okay, let me ignore these sizes for now. Let's figure this out later, because the point is something else. and I'm already confused now. So the important point here is that if I have two matrices, oh, okay, now I see why. So I wanted to have A on the outside. So if I have two matrices, A and B, and they have the right side that they're composable, then the transformations T sub A and T sub B will be composable. And so if I apply one after the other, what I get is the matrix A times the vector B times X. And this is by the definition of the matrix multiplication. This will be AB applied to X. And so this means the composition of T sub A and T sub B is actually the matrix, the transformation of the matrix AB. All right, so now from a previous proposition, and let me just, let's look at which one it was. It was 256. Yeah, where do I write now? I think I can get away with a little bit more space. I hope this is still readable. So by the by proposition 256, the image of TA composed with TB is contained in the image of TA. So, but this is nothing else than saying that the rank that the dimension of the image of TAB, and now TAB is the same as TA composed TB. Let me give this equation here a star. So now I'm just changing TAB to TA composed with TB. That's the star. And then I'm using, let me give this the proposition a red star. And then I'm using this inequality, which is saying that if you have a subspace contains another subspace, then the dimensions have to be less or equal, like they have to be comparable in this manner. So this means this is less or equal than the dimension of the image of TA. But I also know that the dimension of the image of a transformation is exactly the rank of its matrix. Yeah, this is the thing that I wrote on top, and I'm wondering now whether I should have gone through this before or whether you have questions, but then just let me know and we can discuss this. So now, because this is exactly the rank, of AB, we have that by the above equation that this is less or equal than the rank of A. So I'm multiplying a matrix on the right with another matrix. You get that the rank decreases or stays the same. And this is the end of the proof. And I guess, yeah, let's go. Let's look for questions first. Right, I was going to say I want to look for questions first and then resolve this issue with N and M. So because we can compose TA with TB, this means that TB has to go from some R something to R something, and then TA has to go from that to another R. And if you have a matrix, so this is going to be in this box. I'm going to resolve the confusion. Maybe it's going to be important. It's going to be helpful for you in the future. So if you have a matrix of a certain size, let's say m cross n. Let's make this, let's call this B, and let's say this says m cross n. So this is going to have, this is going to be a matrix with m rows and n columns. So this is an m cross n. Then the way that you can apply this to a vector means that you can apply this to a vector x1 to xn if it has exactly n entries, because what you do is you take this as a column and lay it on top of the matrix, and then you multiply them pairwise. So this means this has to agree. And so what we need is that it goes from Rn to Rm. So this means if B is m cross n, then TB goes from Rn to Rm. So these numbers are exactly switched. So the second number is then is the dimension of the domain, and the first, and this number is the dimension of the codomain. So this is probably the easy way to remember. You just have to switch these things. And yes, so then if you want to have A and B composable, these have to match. So we have to have that. What do you do? So if we want to compose, if you want to compose TB with TA, so if you have T sub B, sorry, T sub A composed with T sub B of X, this is going to be a B times X, and B from, sorry, A, exactly from the same rule, has to be of size P cross N. So this means that that AB is defined if we have something of size P cross M times something of size M cross N. So this is exactly as I explained before. This is now composable. Okay, I hope that resolves the issue, and I'm just going to put in these numbers. A is a P cross N. This is an M cross N matrix, and then yeah, then it makes sense that B, in this case, this should be B, goes from N cross M. Okay, I think now everything is correct. Only that I should change this also to a B. Any other questions? Yeah, okay, so the lecture time is up, and the only thing left in this section, which we're going to start with next week, is going to be looking at an example. So we are looking at an example of how this matrix multiplication compares to composition of transformations in case of the d by dx. All right, if there's no questions, then I'll end the lecture. Aditya, you have a question?
Yeah, it's just a quick question about previous part. Could you go to that question where we had like n is equal to 1 and n is equal to 2? and we were comparing.
Yes, yes, absolutely. What was that? This one.
Yeah, I think you passed it. Yeah, right there. Why is n is equal to 2 not injective? I get why it's surjective, but
N equal to 2.
yeah. So why is it not injective?
Oh, so we have, right. So if n is equal to 2, that's a good question, because I think it didn't focus on that while we're discussing this. So the reason that it is not injective is because the dimension of P2R is equal to 3. This is the domain,
Mhm.
and the dimension of R2
Just 2.
is 2. This is the codomain. And then so there was this proposition, which is this corollary to 4.5, which said that it can only be injective if the codomain has a greater dimension than the domain.
Oh yes, yeah. I forgot about that when thinking about this. All right, thank you.
Yes, okay, you're welcome. So I'll just write by corollary 2.4.5. It can't be injective. Other questions? Okay, then I'll end the stream here, or the lecture recording, and I'll see you guys next week. Remember that my office hours are now after the lecture on Wednesdays, but it's another announcement.